Hello students, today we will discuss a device that is called Wheatstone Bridge. A Wheatstone Bridge is an arrangement of four resistances to find one of its resistance with the help of three in an accurate way. So let us consider its working. As I told you that Wheatstone Bridge is a combination of four resistances. So I am just taking that I have four resistances and I connected them to form a quadrilateral. Let me call this resistance as P, this is Q, this is R, this is S, and I will connect this combination with the help of a battery of EMF E, and I will connect a galvanometer along this diagonal and see that the galvanometer has a resistance of G and this. So as you can see that it is one diagonal of this quadrilateral and this battery is also connected across this diagonal of the quadrilateral. So now if battery delivers I current to the circuit, let us take that this current I1 is flowing in the resistance P. Now as this I1 will reach this point, there will be two branches, so I am just assuming that Ig is the current that goes in this branch, so the remaining current will be I minus Ig and that will flow through this resistor Q. So this is the current I minus Ig. Now just look at this resistance. Let us consider that this current is I2. So I2 will flow through R, the Ig is coming through this branch, and from Kirchhoff's first law, if both the currents are incoming, so the outgoing current will be I plus Ig, and this is I2 plus Ig. And if you will look at this point, once again at this junction, I can apply Kirchhoff's first law, that is called Kirchhoff's current law. These two currents are coming, so I will add them, and if you will add, you will get the net current as I1 plus I2, because this one is I1. So the net current is I1 plus I2, and I can write it as I, since I is splitted into I1 and I2. So here I can also write I as I1 plus I2. So this is the net current. Now I will apply the loop law or Kirchhoff's second law in the two loops, as you can see. So first of all I will take this loop and I am going clockwise. So I will start from here, and you are well aware of the Kirchhoff's voltage law. So if I am going in the direction of current, this is the resistor, so the voltage drop will be minus of I1 into P. Now again there is a resistance of G and Ig, and I am moving in the direction of current, so it will be minus of Ig into G, and here the voltage drop will be I2 into R, but as we are moving opposite to the direction of current, so it will be positive, so this is I2 into R, and once again Ig is the same point, so I will equate it to 0. This is KVL in loop 1. This is my first equation. Now I will apply the same Kirchhoff's second law in this loop. So just consider, I will start from this point, I am going in the direction of current, so I am going to apply KVL in loop 2. So just check it, voltage drop will be current, that is I1 minus Ig into Q, and this will be minus since I am moving in the direction of current, and here we are moving against the current, so the voltage is IR, the total current is I2 plus G, Ig and S, and when you will move like this, you are again and going opposite to the direction of current, so it will be positive voltage drop, and the voltage will be current, that is Ig multiplied by resistance, that is G, and once again you reach the point, so this is equal to 0. So we have applied the Kirchhoff's voltage law in these two loops. Now if the arrangement is taken, or you can see that the values of P, Q and R are chosen in such a way that this galvanometer shows zero deflection. That is, if the current in this branch is zero, then it is called balanced bridge. Then this is called balanced bridge. So this is the condition of balanced bridge, that this bridge is said to be balanced when there is no current through this arm or galvanometer shows zero current. So if you will put this in these equations, so I am just solving it for balance condition. So this first equation will become minus of I1P, this will become 0 plus of I2R, and that is equals to 0. And if I will further simplify it, I will get I2 by I1 as R by P. This is my equation number 3. This one was first, this one is second. Now once again I will apply this value in this second equation in loop 2. So your Ig is 0. So this term will become minus of I1Q plus this Ig is 0. So this is I2S, and this term will also be 0, and that is equal to 0. And if I will further simplify it, I can get I2 by I1 as S by Q. This is my equation number 4. And as you can see that these left hands are equal, so right hand must be equal also. So I can write R by P is equal to S by Q, or I can write that R by S is equal to P by Q. So P by Q is equal to R by S. This is the condition, or this is the relation among the four resistors where the bridge is balanced. So if you know any of the three resistance, you can find out the unknown resistance. In general, the unknown resistance is connected across this terminal S, and that is why this R is most commonly called unknown R in this Wheatstone bridge. So remember that in the balance condition of Wheatstone bridge, the ratio of the resistance you can also understand like this. The ratio of P to Q is equal to the ratio of R to S, or in other words, the ratio of P to R is equal to the ratio of Q to S, and in both the way we can apply the balanced bridge condition. Now we will discuss the applications of Wheatstone bridge, and that is a meter bridge. So we can say that meter bridge works on the principle of Wheatstone bridge, and it is also used to find the unknown resistance as an experiment in the laboratory. So let us see. In a meter bridge, a 1 meter wire is placed over a wooden scale. This wire is made up of constantan or manganese, and so it is a 1 meter wire. Let's take the length as 100 centimeter, and I will connect this wire with the help of two L-shaped strips of copper. In general, the aluminum strips are used, and there is one another strip. I will connect a resistance box here. So this is your resistance box, with the help of which I can apply a resistance of desired value. So I am just taking the resistance applied by the resistance box is R, and unknown resistance, or the wire whose resistance is required, is connected across this terminal. Let me call the wire as AB, and from the middle of this we will connect a galvanometer with the help of a jockey J. So when you will touch this wire with the help of a jockey, so it will divide the wire in two parts. And when you will divide the wire in two parts, then we know that each wire has its own resistance. So if the wire is divided into two parts, so this part will have some resistance and the remaining part will have another resistance. So we are having four resistances, as you can see. One applied from resistance box, the one is unknown resistance X, and the part of this wire are we having like two different resistance. So we are having four resistances basically. And this is the diagonal, as you can see, this 1 2 resistance, this is third, this is fourth, and this is the diagonal. So the galvanometer is connected in diagonal, and I will supply the current in this circuit with the help of a battery. Now consider that the jockey is placed at a point where the middle of the galvanometer is straight. It means there is no deflection in the current. If you will move just left or right to that point, the galvanometer will show deflection. It means the current will flow through this branch, but there will be a point in between A and B where there will be no current in this galvanometer, and we know that this is the condition of balanced bridge. So if there is no current in the galvanometer, I can apply the condition of balanced bridge. So from the condition of balanced bridge, I can equate the ratio of the resistance. So as I told you, this resistance divided by the resistance of this part. So I will write this is the resistance of part AJ of my wire. Now for this I can equate the unknown resistance to the resistance of this part of wire, and that is RJB. So this is the resistance of part JB of the wire. Now I can do like this. This is R by S equals R of AJ part and resistance of JB part. This is equation number 1. And we know that the resistance of a wire is given by rho L by A. The cross section of this area is uniform, so A will remain constant. So from this formula I can calculate the resistance of both the parts of the wire. So I can write for part AJ and resistivity, that will remain constant. The length is L, so just take this length as L. So if the whole length is 100 centimeter, the remaining length will be 100 minus L. So for this part, the length is L and the area is A. Similarly, for JB part, for this part, the length is 100 minus L. So this is resistivity. Length means 100 minus L and divided by A. So these are the values of the parts AJ and JB, and I will put the value here, and when you will put these values here, you will get R by S equals L by 100 minus L. Since S is my unknown resistance, so S is going to be R times 100 minus L by F. So with the help of this formula, we can find out the resistance, that is the wire of the resistance that is connected across these two terminals. Once you know the balancing point, since I told you that this wire is placed just over a wooden meter, so we can easily find out the length from this terminal. So once you know L, once you know the resistance applied from the resistance box, we can easily find out the resistance of this unknown wire with the help of meter gauge. Now let us solve few numerical problems based on meter gauge. So we will start with the first problem. So as per question, the null point is found at a distance of 60 centimeter. So I can apply the balance bridge condition, that ratio of R to S is going to be 60 because it occurs at 60, and the remaining length will be 40. So this is in the previous condition. So this is in the present condition when the balance point is found at a distance of 60 centimeter. Now as per the condition, when you will introduce a resistance of 5 ohm in series with the resistance S, the balance point shifts to 50 centimeter. So when 5 ohm is connected in series with this S, the total resistance will be S plus 5. So for the next condition, R remains unchanged. This is resistance S plus 5 ohm resistance in series. So net resistance is S plus 5, and now the balance occurs as 50. So the remaining will also be 50, and this is equation number 2. Now you can divide these two, and if you can divide these two, you will get S plus 5 divided by S equals to 3 by 2. On simplifying, you can do it easily, and when you will simplify this, you will get S as 10 ohm resistance. Just simplify it and you will guess the value of unknown resistance as 10 ohm. Now since the value of S is known to me, so I can find out the value of R. So I will put this value of S in equation number 1, and this is R equals S, that is 10 multiplied by 60 by 40, and if we will simplify it, this is going to be 5, this is 15. So this is the solution that was given of this question, and the values of R and S are 10 ohm and 15 ohm respectively. Now we will see the next problem, and that says that a balance point is found at J and the length AJ is L. So for the given circuit, if I will apply the condition of balance bridge, so this R by X, that is the ratio of resistance, is going to be L, and the remaining length is 100 minus L. This is my equation number 1. Now the question says that these two R and X both are doubled and exchanged. So in place of R we will write 2R, and in place of X we will take 2X, because both are doubled, so R will become 2R, X will become 2X. But since the resistance are exchanged, so in the place of R we are applying X, and in the place of X we are connecting R. So if you will double and exchange, the ratio will be twice X by twice R. Since both are doubled and exchanged, so now there will be X by R, because you know your X will be in the left and R will be on the right, because both are exchanged. Now let that new balancing length is at L dash, so it is my L dash, and the remaining length will be L dash, 100 minus L dash. This is when both are doubled and exchanged. So now I will simplify these two. If you can just see it, I can simplify, write it as 2 will cancel out, and I can write R by X as 100 minus L dash by L. This is equation number 3. And as you can see that both the left hands are equal, so I can quit right hand side. So it will become L by 100 minus L equals to 100 minus L dash by L. Now you will cross multiply, and if you will simplify, you will get L dash as 100 minus L. So this is the new length when both the resistance are doubled and exchanged. Now the next part says that what will happen to the balance point when galvanometer and battery are exchanged. So as you can memorize in the previous Wheatstone Bridge concept, I told you that battery and galvanometer both are connected across the diagonal of the quadrilateral. So if we will exchange the quadrilateral under the condition of balance bridge, there will be no effect. Once again the galvanometer will show zero deflection. It means by exchanging the battery with the galvanometer and galvanometer with the battery, there will be no effect on the balancing of Wheatstone Bridge.